Sri Gurubhyo Namaha children, welcome to online class. Today's class we are going to learn about the standard electrode potential of inner transition element. So now the standard, what is meant by the standard electrode potential, or what is the use of standard electrode potential? From this you are going to find out the reducing property as well as the oxidizing property of the metal which involved in the redox reaction. You know that already in the redox reaction the oxidation and the reduction is going to taking place. So the oxidation means the loss of electron, and now you see that redox reaction involve the transfer of electron from one reactant to the another reactant. Because how the transfer of electron is going to take place? By loss of electron and gain of electron. Now if you go for example, A and B involved in this reaction, here A is going to lose electron to undergo the oxidation reaction, and the B undergo the reduction reaction by gaining the reaction what the A is going to lose. Understand, by this way the redox reaction is going to take place. That is the transfer of electron. Transfer means one element has to lose its electron and another element has to gain the electron. So by redox reaction. So such reaction is always coupled. So what is that couple means? Oxidation and reduction is going to take place simultaneously. So the element which undergo, the substance which undergo is oxidized must be reduced by another element. So the substance which are undergoing the oxidation or oxidized, they are act as an powerful reducing agent. So the element which undergo oxidation, they act as powerful reducing agent, and the element which reduces with undergo or which act as an oxidizing agent. By this, so by using the standard electrode potential, we can able to find the oxidizing and reducing power of an element. By standard electrode potential, we can calculate or find out the power of oxidizing and reducing power of the element of transition element. And next case, so what is that standard electrode potential? What is meant by standard electrode potential? By this way you can find out the standard electrode potential for every element. For the molecular hydrogen, now we are going to take the molecular hydrogen under the condition of 1 atmospheric pressure and 273 Kelvin. So that is under 25 degree Celsius and 1 atmospheric pressure. The molecular hydrogen is going to oxidize in solution in water, or it oxidate solvated to give proton H plus ion. Understand, the hydrogen is going to oxidize to become what? H plus by loss of electron, because the hydrogen has the atomic number 1 electron and 1 proton, there is no neutron, it loses the electron, it become what? Proton alone. So that H plus ion is expressed as what? Proton. So the proton, the EMF value, the stage at which the proton is solvated, that EMF is called the standard EMF or the standard electrode potential, that can be denoted by E0. The EMF is, or the electrode potential can be expressed in E, and the standard electrode potential can be expressed by E0. By this value we are going to find the standard EMF for every element. So based on the standard EMF, the metal with large negative value, they are act as a powerful reducing agent. The metal with a large negative value, The metal with large negative value is act as a powerful reducing agent. So by this we can calculate by the EMF value whether the element is act as a power reducing agent or oxidizing agent. So if the element with a large negative value, that case what? Large negative means they loses the electron. They losing the electron, by this way they can act as a reducing agent. Understand? By this way they are going to reduce by itself. And next one, see now you can see that compare the reducing property of the element in 3D series. Now you can given the value for titanium is going to reduce, titanium ion is going to reduce to titanium metal by giving minus 1.69. So now this is the large negative value. So while comparing 3D series, titanium, vanadium, chromium, manganese, iron and cobalt, nickel, the titanium has large negative value, so that it acts as a powerful agent. Now you see this, here the chromium, the copper has what? Positive value, so it won't act as a reducing agent. And next, the next one minus 0.76. The next largest value is what? Zinc. Now you can see this. So the standard reduction potential, the standard reduction potential for metal ion to metal. So now we are going to see from titanium to zinc, the standard reduction potential value is approaching less towards negative value, when if you copper has what? Positive reduction potential. So what we learn already, the large negative value has act as a powerful reducing agent, but here you can see that the copper has positive, so it doesn't so the copper 2 ion is going to reduce to copper. So why it is not act as a reducing agent? Because we will see that the copper 2 plus is, the copper, elemental copper is more stable than what? Copper 2 plus. Because of this, the copper cannot act as a reducing agent. And next you can compare this. See this comparison, why there is a difference in, so in the elemental copper. So now you can see this, there is a steady reducing in, and there is a steep decreasing in manganese and zinc. Now you can see here, so that the elemental copper more stable than 2 plus, so that there is 2 deviation. What are the 2 deviation? One with manganese. So now you see this, there is a steady reducing, decreasing in the value. Now you see this, but there is a steep variation among this manganese and zinc, because of the extra stability, because of the extra stability. The manganese has D5 and zinc has D10 electron in the outermost orbital. So the D5 off filled configuration and D10 fully filled configuration. This become what? D5 now you see this become D5 and here D10, off filled configuration and fully filled configuration. Both are, they can show the extra stability because they cannot lose the electron in this way. So there is a variation, in this. The here you can see the regular trend of the reducing property, but due to this Mn2 plus and Mn2 plus and zinc 2 plus, here Mn 2 plus ion and zinc 2 plus ion. After losing, they show the extra stability. By this way they can show there is a variation in the reducing property, decrease in the reducing property. And next, now you can see that the transition metal with higher oxidation state. High oxidation state is oxidizing. So now you can see that for comparing Fe3 plus is moderately strong oxidant when oxidized to Cu2 plus. Now you can see that, so Fe2 plus ion, Fe3 plus ion is going to reduce to Fe2 plus, and the E naught value of this is 0.77 volt. The E naught value of this, the ion Fe3 plus is going to reduce to Fe2 plus, and then copper 2 plus is going to reduce to elemental copper, and the E naught value is equal to 0.36 volt. So now while comparing this, which one? The higher oxidation state, the iron is in the higher oxidation state plus 3 is going to oxidize copper. Understand? So that while compare the standard electrode potential, iron has higher EMF value, standard EMF value, that is 0.77 volt, then what? The copper has what? 0.36 volt. Now the higher oxidation states all act as an oxidizing agent. Now here the iron is going to oxidize the copper ion to copper, metallic copper, then only the reaction is what? Feasible. Then only, so here that iron is going to helpful in reducing copper ion to copper electrode. And now you can see that the Mn2 plus ion, the standard electrode potential of the cell. So now it is going to the higher oxidation state. Now higher oxidation state, see the reduction value is going to be less when compared with the last table, in that the oxidation state is +2 oxidation. +2 oxidation, they all can show more power of reducing agent. Now here the metals all become +3 2. The metal become +3 to 2 plus. So here the stability between the metal in +3 oxidation and +2 oxidation, the potential value. Now you see that the stability of the element in 3D series, titanium, vanadium, chromium, manganese, iron and cobalt. Now you see this, the positive value of manganese and the positive value of iron, because in Mn2 plus half filled configuration to the extra stability, it can act as an reducing. But in this case 3D4 in manganese, in Mn3 plus the configuration is 3D4, so they are readily to lose the electron, they are undergoing the oxidation than one reduction reaction. So now the cobalt also more stable when 3 plus 2 plus ion. So they can show that positive value, EMF value is positive. So the positive, the chromium 3 plus ion. So now see this, the negative value of titanium and vanadium indicates the higher oxidation state or preferred. So now while compare with the other element, so the titanium and vanadium and chromium are preferred with negative oxidation, because the negative value, higher the negative value, they can act as a powerful reducing. So even in the higher oxidation state, the titanium, vanadium and chromium are preferred to act as a reducing agent, but you compare with manganese, iron and cobalt, in the higher oxidation state they cannot able to act as a reducing agent. That can be given in this tabular column. Now you compare this. With the graph. Now already you know that, see, the value of the reduction is very low value, it is given 0. Higher value minus 0.5. In that last previous one we know that 2.5 minus 2.5, so very low value. So now what is increasing? In the higher oxidation state, the chromium and vanadium and titanium, they are preferred to be a reducing agent, and when compared to manganese, iron and cobalt. Now the manganese has D4. So what is that? Manganese 3 plus. The higher oxidation state, manganese 3 plus, the electronic configuration is D4. So the what is going to be dropped? The value is going to be dropped from manganese to iron due to the electronic structure. And the manganese has 3 plus, manganese 3 plus ion has what? 3D4 configuration, and manganese 2 plus ion has 3D5 configuration. So due to this extra stability, extra off-filled d orbital, that makes the reduction of manganese 3 plus is very feasible one, and it possesses what is that? Plus 5,1. Now you see this positive value. It become what? Positive value by showing this. So what? By having the of extra stability is what? Mn2 plus, but in Mn for 3 plus, the extra stability is going to be associated with to make the feasible one of the higher value of what? Positive value of 1.15 volt. Understand? So by this we can measure or we can calculate the powerful, or which one is going to act as a powerful oxidizing agent and which one act as a powerful reducing agent based on the electronic structure as well as the oxidizing state of the metal. By this way you can learn the standard electrode potential. So the standard electrode potential can be measured by hydrogen electrode potential. By this we can able to calculate the oxidizing power as well as reducing power of the transition metal. So thank you for watching this video, children. So you want to receive the latest update of the lesson, please press the subscribe button. Thank you.